This is the second in a series of videos that I'm posting showing how I'm going about designing and developing a drop-in SRAM card for the Altair 8800 vintage computer. It's going to be a 64k card and it's intended as a low-cost alternative where it can be used in place of existing expensive or hard-to-find memory cards if users need to do specific testing or just for everyday use and want to use a lower cost card rather than their expensive originals. The reason I decided to do this is because I'm currently investigating bus noise on the Altair and I needed a fairly low cost card that I could use for that testing. The testing is fairly intrusive and I didn't want to do too much messing about with the vintage cards that I have. So I decided to design one from scratch, and that's what this series of videos will be documenting. In the first video I went over the general approach that I was going to be taking for the development, and in this video I want to look in more detail at the control logic for the card. So these are the signals that the Altair sends to the card when it wants to write data to the card or read data from the card. As I mentioned in the previous video, the Altair is a little bit quirky in the way that it performs some of these tasks, and in particular there's a different way that it accesses the card when it's in manual mode compared to when it's actually running a program. In manual mode, the control signals and timing come from the display panel on the Altair, whereas when it's running, of course, then it comes directly from the processor. So as I explained in the previous video, these control signals are used to control various aspects of the card. That includes reading and writing from and to the array of SRAM chips, but it also controls the latching of the data, which is required so that it can be displayed on the front panel, and also the control of the tri-state buffers on the card to allow data to be put onto the data bus. So I won't be able to use it exactly as it is in this form because the requirements of my memory chip are slightly different, but the control logic did seem to make a lot of sense, and of the various schematics I have, this was the one that was more applicable to this application, so it's the one that I decided to use as the basis. So I've redrawn the part that is relevant to what I need for the new card. So this is what I've ended up with. Essentially it's the same with a few small differences to suit what I need. It's not complete. I will need to modify this slightly in the next video when we look at the mapping of the card. But in terms of the logic to drive the card, then this is the starting point. Very similar to the original card, we have a series of OR gates here that are used to decide if and when the various control signals need to be propagated into the card. The incoming buffers, which I've retained simply because they give the correct state of the signals and it simplifies the logic further down the line. So the signals we need to end up with for this card are output enable, read write, latch and chip select. The chip select line will be a bit more complicated and I'll explain why in the next video. Latch is just a signal to latch the data that's coming out of the RAM chips into the output latch. Read write is obviously to control whether we are reading from or writing to the RAM chips, and output enable is a control line that determines if data is currently being put out onto the data bus. On the incoming signals we have the same as we had previously, and there is a definition for all these that you can easily find on the internet, but essentially they are used to tell the card exactly when it's required to perform certain tasks, and also to make sure it doesn't perform those tasks when it's not supposed to. We have control signals such as memory write that are used to tell the card what mode to run in, and ultimately it's what controls the read-write line. Q1 is the control signal from the CPU that basically says that everything is ready and the card can proceed. P-Sync is used to synchronize the overall operation of the machine. You can look in more details at what each of these does. It does vary slightly with each card, but it's really the bus master control lines that are used to allow the CPU card to individually talk to each card that you may have installed. What may seem a bit odd on this, and it's the same as the original card, I retained it for the same reason, is this up here. It seems a bit odd that we're using D07 as one of the control signals, and in fact we're using it as one of the most important control signals. If you ever try to make a memory card for an Altair, or any other card come to that, you'll know that in particular when you have a line such as SMMR, which is used to determine when a memory fetch is being executed, you'll know that the operation of this on the Altair is very weird, in that when you're running a program, this line works fine and the timing of it is fine. But if you're trying to get a card to work, you might find that in manual mode you can't get the pulse that is required to read and write from the RAM to work correctly. And almost certainly that is because this line, which is a status line that originates out of the CPU, doesn't occur soon enough, and that's because of the design of the CPU card on the Altair. So we'll have a quick look at that. So this is the schematic for the CPU, and the bit that we're interested in here is the control line that comes out of D7. And it might seem strange that, as I say, it's a control line. It's essentially used as a status byte that the CPU outputs when it wants to perform certain tasks. So I've zoomed this diagram in to look at the bit in more detail that we're interested in here. And what we end up with is this part of the schematic, and hopefully you can see this fairly clearly. I've highlighted the path that we're interested in. So this status byte that's output, and in fact if you look at the timing diagram, you'll see that fairly early on in the cycle you'll see this status thing here, which looks a bit weird, but although it says status, it's actually used in the memory card as a control line. But the line that we are interested in here is the SMMR line, which is up here. And you can see that the way that's generated, if you follow it back through the buffer and back to this device. This is a register SIM device that's actually used on the original memory card. And then follow that back through, it originates at D7 in the CPU. So in other words, this status output was originally D7, went through this latch, and then it goes up to this latch here, where it's ultimately, when it's required, latched out onto the main backplate as SMMR. This latch is controlled through this line, and if you look at the part of the schematic that controls that, you'll see that it's controlled, and this data is latched in various cycles from the master control when it wants to perform certain tasks on the backplane. The problem with this is it doesn't occur in time for the memory card. By the time this signal is asserted in the manual mode, it's fine for when the systems are running a program, but in manual mode this doesn't happen in time, and you'll find that the pulses that you want on your memory card don't seem to be working. So the way that it's implemented on the memory card, and the way that I'm going to use it as well, is when we look at these various lines. Now PD bin is responsible for the latching of SMMR on the CPU, or it's one of the control signals that dictates when that will happen. And so for various control signals we want on our memory card, we want the same signal. We want this SMMR, but we want it sooner than the CPU is putting it out. So what we do, instead of waiting for SMMR, is we use D7, and we use D7 as an early SMMR driven by PDBin, because as soon as the data comes out of the CPU and we're waiting for it to be latched, we may as well just use it directly because it's already on the data bus, so we might as well make use of it. So that is what we're doing here, is we're using D7 as a preemptive SMMR so that it's available sooner, and that allows the card to work correctly. In manual mode, if we wait for SMMR, as I said, then it will be too late by the time various things are supposed to happen, and the memory card either won't work at all or it'll be very flaky in its operation, and you'll find that various pulses don't happen when you expect them to. Okay, so that's the reason why we've got this sort of weird setup with D7. If we were running a monitor program, then we could get rid of this and just rely on SMMR, but in the Altair we need an arrangement like this just to make the timing work. Okay, so that gives us our overall circuit for the control logic. As I said, I will have to change this slightly when I start looking at the card decoding, but I'll go into that in the next video. But for now, the logic makes sense, and this is what we're going to test today. So next step is I'll get the Altair back onto the bench. We'll have a look at how I've cobbled this together to do some testing, and then we'll look at the signals on the logic analyzer. So this is what I've put together so far, and it's this circuit built onto a breadboard, and I've hooked the analyzer up to the points that I've circled. So essentially it's the same points we were monitoring in the previous video, with the addition of this separate chip select line. So I'll get the analyzer switched on, and I'll move the camera so we can see the screen, and I'll take a few captures of the data just to check that it's still the same as we had in the previous video. Okay, so I have the analyzer hooked up. The Altair is set and ready to go using the circuit on the breadboard. The analyzer is set to trigger on test point 2, which is essentially our memory read line. So I'll arm the analyzer and then perform an examine, which should trigger the analyzer, and we should capture a memory read cycle. So we've captured that, and we can now compare that against the expected signals on the diagram we looked at in the first video. Bear in mind this time though that these are coming from the circuit that's built on the breadboard and not from an actual memory card. So we're just trying to confirm here that the circuit works and it performs and behaves as expected. So the first thing we expect to see when we look at the timing diagram in the manual is sync going high, and indeed that's the second trace down. P-sync is going high, and if we follow through the various signals, and I'll just put this here so you can have a quick look at it, and then you can freeze the video if you want and compare them. So you'll see that all the signals are correct, and what we end up with is exactly what we're looking for, and that is we have a chip select going low, we have test point 2, which is our read signal going high, and then the various other signals that control the latching and the output of data onto the data bus are also correct, which means that in its current form this is very close to what we need for our new device. And in fact, if we have a quick look at the timing diagram for the memory chip, again I'll just put this here so you can see how it compares. So the top diagram is for read, so it's the read timing, and then for write we have this one. So you can see that for the one we're looking at now, the chip select line needs to go low, output enable also needs to go low, and that's what test point 3 is. So you can see that we're getting chip select going low, which will output data onto the internal data bus on the memory card, and then test point 3 is going low, and that will latch the data into the output buffer on the memory card, and then the control line to put the data onto the actual data bus, which is test point 5, is also working as it's supposed to. It's a bit confusing looking at this because for whatever reason the Altair performs certain functions more than once when you're in manual mode. So this cycle effectively ends here, and as you can see at that point all the signals are exactly as we need them for the new memory chip. So in other words, what we have here is the logic circuit that we need to drive the new chip, at least in the memory read mode. So what I'll do now is change the trigger to look at the memory write line. So I've actually got these predefined, so it saves having to reconfigure the entire thing. Okay, so it's now armed to trigger on the memory write line, so I will do a deposit, and you can see that we have indeed captured data. The other strange thing with the Altair, as you can see, is certain lines stay in a fixed state for a very long time, and that's just because those signals are generated by the control card, and they do have a very long duration. Some of these control signals take up to 200 microseconds to complete. And in fact, if we now do a similar thing, what I'll do is I'll rearm the analyzer, but instead of hitting deposit or examine, I'll get it running. There's no programming here, but because there's rubbish in the memory, it will do something, and that usually involves accessing or trying to access memory. So you can see now that the control lines all have fixed durations, and that's because they're being controlled properly by the processor rather than by the front panel. As I said, the front panel operation is a little bit weird sometimes, but you can see normal run mode is doing what you'd expect. Okay, so that's it for this video. In the next video we'll look at the memory decoding and how to generate the 2 chip select lines that we need for the 2 memory devices that we're going to have on the card.